Hey, what's up, everybody? We're about to go over some chemistry and things you should know so far. First thing I'm going to talk to you about is drawing some Bohr models. And this is a homework assignment, okay? And you're going to do this with me on your own piece of paper and then turn in a picture of it, all right? So the first thing we're going to do, we're going to talk about Bohr models. And I want you to know or to remember that Bohr models match the periodic table. So if we're looking at this periodic table, wow, I gotta back off of that, don't I? If we're looking at this periodic table right here, then we can predict what the Bohr models will look like. Now, first of all, start with some simple Bohr models. How about a Bohr model of oxygen? Okay, so I would say, hey, how many circles would a Bohr model of oxygen say? And you would say 2, because to get to oxygen you have to go down 1, 2 periods. So it's going to take 2 circles to make it. And then I would say, how many valence electrons or outer electrons would oxygen have? And you'd say, well, 1, 2, 3, 4, 5, 6, because you have to go over 6 boxes. So in other words, oxygen is down 2 over 6. So its Bohr model would look like this. It would take 2 rings, and then in the outer ring there would be 1, 2, 3, 4, 5, 6. And you also know that in the inner ring it holds 2. So oxygen would be 2 and 8. So now I'm going to ask you to turn in number 1. How about very simply show me a picture, a Bohr model of sulfur. So sulfur is going to be number 1. Show me a picture of sulfur. All right, great. Now let's keep moving. Now, when Bohr models get bigger, things change. So if we were doing a Bohr model, you know that once we get in here to the D's, it's a little bit different. And the reason is that these d orbitals don't stretch out all the way as far as you would expect them to. So let's say we were going to do a Bohr model of iron right here. We'd work our ways there. It's going to take 1, 2, 3, 4 circles to do iron. So I'm like, okay, 1, 2, 3, 4 circles to do iron. And as we work our way there are 1, 2 boxes in the first row, or the first period. So we got 2 electrons in our inner shell. And then in period 2, there are 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. In the second and third period, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we got 2 and 8 and 8 so far. And then now, remember, we're working our way here to iron. We're working our way here to iron. Now we're down here, so we're in the 4th row. We've got 1, 2. Okay. 1, 2. So we've got 2, 8, and 2 so far. And then when we move in here to the middle, these are different. All of the transition metals act like they are up 1 period. Okay? So we have 1, 2, 3, 4, 5, 6 dots now to get to iron. But these electrons are only in actually the 3rd period. So we go back and we say, I'm going to make X's for these so you can see that I added them later. 1, 2, 3, 4, 5, 6. So those 6 would go right here. And iron would be 2, 8, 14, and 2. Now I'm going to warn you, if you start Googling these answers, I'm going to bust you, because there are different ways to model these, different from the way I'm teaching you now, okay? And if you Google it, you're going to get some answers that are different. So make sure that you do it this way and that you actually do it yourself, because Googling it is going to mess you up. All right. Now let's take a look. Let's keep moving. So you've drawn me sulfur, and now what I want you to do is I want you to draw me a Bohr model of copper. So the second problem for you is draw me a Bohr model of copper. All right, now, when we look at the periodic table, we can break it up into the different orbitals that exist. Now these guys over here, these two tall rows, right here that I'm outlining, these two tall rows, and we put helium, you take helium and we put it right here, okay? We just include helium, we include it over here. These guys are called the S's, all right? And then these 6 tall rows over here, these guys are called the P's, and these guys right here are called the D's. Now I've told you many times, and then down here on the bottom, these are the F's. Now I've told you many times you're not going to be responsible for drawing the atomic flower, but you are responsible for writing Aufbau sequences, okay? So I'm going to write an Aufbau sequence for vanadium with you, ready? It would start out like this for vanadium. We just go across the periodic table like we're reading a book. So boom. How many, and here's the periods, 1, 2, 3, 4. So 1, and there's 2 S's, so you'd write 1s2. Okay, we're doing vanadium. And then the next thing, now you're down here, the 2s2. And now you're over here still in the 2's, but now you're in the P's. 2p, how many are there? 6. 2p6. And you're down here in the third period, 3s, how many are there? 2. And now you're in the P's. How many P's are there? 6. 1, 2, 3, 4, 5, 6. 3p6. And then now, like I said, we're still trying to make our way to vanadium. All right. Now we're down to the fourth, 4, and this is the S's, 4s2. And then now we're here, boom, boom, boom. We're in vanadium. Remember, these act like they're 1n. 3d3. That's vanadium. Vanadium's Aufbau sequence. What I want you to do is write me an Aufbau sequence for zirconium. So an Aufbau sequence for zirconium. So number 3 is going to be an Aufbau sequence for zirconium. And you can do that, I guarantee you. All right, let's keep moving on. Now we're going to talk about ELDs, or electron level diagrams, and these are really just another way to model the atom. They match the Bohr models. Really, they match the atomic flower, and they match the Aufbau sequences. Now, there are 2 guys, and you need to know what these guys, what their deal is. Hund's rule, you need to know what that means, and you need to know what the Pauli exclusion principle is, all right? You need to know what these things are, okay? Now, I'm going to follow Hund's rule and the Pauli exclusion principle, and we are going to model right now, we're going to model an atom of, let's see, I've got some 3Ds here, so I'm going to do nickel, all right? I'm going to do nickel, all right? Nickel. If I look on the periodic table, and now I'm going to phrase this a little bit differently. If I look on the periodic table, I can tell you that nickel is in what position? Nickel is in position 3d8, okay? And you should understand that. If you don't, get to work. Nickel's in position 3d8. So I'm going to work my way up this chart, starting from the inside and working my way out till I get to 3d8. 1s up, down. That's 1s2. The Pauli exclusion principle says only 2 electrons can fit on each orbital, and they must go in opposite directions. So that's the Pauli exclusion principle. 2s2, 2p up. And where does the next one go? That's right, it goes up here. That is Hund's rule. Hund's rule that says you have to go x, y, z on your orbitals before you double up. Okay, so 2p, 1, 2, 3, 4, 5, 6. This would be neon if we stopped right now. Sodium, magnesium. Now up, 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 following Hund's rules. Down, down, down. This would be argon. And now this is potassium, of course, and this is calcium. And now we've got to work our way across the D's until we get to nickel, okay? So here we go. I'm going to do that with you. Let's see if I can fit it all on the screen here. There we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Now, opposite, opposite, opposite. This is what nickel looks like. Again, make sure you follow my rules, because if you Google it, it can get a little bit funky. You can give me a different answer that will make it very obvious that you Googled. So here's what I want you to do. I'd like for you to do iron. I'd like for you to do iron. So the fourth problem is copy a chart and do an ELD for iron. Alrighty. Another thing on our test is Bohr's model for the hydrogen atom. Now you'll have an ed puzzle on this, or you already have had an ed puzzle on this. But the basis is this. Electrons stay as close to the center of an atom as possible. And if you heat up an atom, they will jump out into these higher orbits. That's how an atom absorbs heat energy. When you take it away from the heat, the electrons lose their energy and boom, 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 jump back to the middle. Well, when they jump back to the middle, they give away the heat energy in the form of light. And we know exactly what wavelengths of light are given off by electrons that fall through certain orbitals. So for example, if you look on here, if an electron falls from this energy level to this energy level, so if we start from the middle, this is 1. These are just the layers of a Bohr model, like 1, 2, 3, 4. So if this electron falls from what we would call energy level 4 to boom, boom, to energy level 2, if an electron falls from there to there, it gives off a certain amount of light. If it's from N4 to N2, the wavelength of that white light is 486 nanometers. Now what that means as far as the math is concerned, when you change it to scientific notation, it's 4.86 times 10 to the negative 7th meters. So that fits right here. 4.9, just below it is 4.86. So that would be blue-green, a bluish-green light, right? So now looking at this, I'm going to ask you, what color of light would be given off from an electron that fell from energy level 6 to energy level 2? All right, and you would write down that color for your answer. Energy level 6 to energy level 2. All right, let's keep rolling. I'm going to ask you 3 quick questions really quick. If nickel is in position 3d8, I want you to name the position of these atoms in order. Give me the position of strontium. Give me the position of chromium. Give me the position of germanium. So we got 1, 2, 1, 2, 3. Nickel is in 3d8. So if we call this its position on the periodic table, give me the position for strontium, chromium, and germanium. All right? All right, that's it. So basically this test is about modeling the atom. And you need to know all the different ways that we model the atom. You also need to understand the structure of the atom, like where the protons, neutrons, and electrons are and what their charges are. You also need to remember what isotopes are. Those are in our notes, and we worked with those. Isotopes are atoms of the same element that have different masses. And the reason they have different masses is because they have different numbers of neutrons, okay? And you need to be able to write isotopes. For example, if we were writing an isotope of magnesium 25, we would say 25 over 12 mg. All right, this is the mass over the atomic number and the symbol. Or you could write magnesium dash 25, okay? So I would ask you to write this type of symbol For neon 12, I would ask you to write this type of symbol for potassium 40, and I would ask you to write this type of symbol right here for, how about uranium? This is really famous, 235. That's it. Hope you did do this homework.